Hello, students. In this lecture, we need to talk about pH and pOH. So in the last lecture, we did a bunch of math to discover the concentration of our hydronium and the concentration of our hydroxide in our solution. And we took a look at a chart to understand what those concentrations meant in terms of, is the solution acidic, basic, or neutral? And then we said, isn't there an easier way to do this? And I said yes, and that's the next lecture, and here we are. So let's take a look at the pH scale at the bottom. So what we can see is that acidic solutions have a pH that's less than 7. So we're over here in the acidic zone, pH less than 7. And basic solutions, which are also called alkaline or alkali solutions, have a pH that's greater than 7, so this way. And neutral solutions have a pH that is about 7. And if you have a professor that's a super stickler, they'll say exactly 7. But if you have a pH that's 7.01, it's pretty neutral. Okay, so what you might notice about the pH scale is over here on the basic side, what we have are a lot of cleaners, things that we use to clean the house or clean our bodies or to clean the drain. And drain cleaner is typically concentrated potassium hydroxide. So you can see right there that OH, that hydroxide, that's definitely going to be a base. And over on the acidic side, what you'll notice is we have a lot of things that we like to put in our food or eat as food. And this makes sense when you think about the things that we put on our food. Like we like lemon chicken or orange chicken, or we like tomato sauces, and those have an acidic or a tart taste to them. And if you've ever watched a cooking show, one of the things that judges sometimes say when they're having a baking competition is that this is too sweet and it lacks some balance, or it lacks some acid. And what they're saying is that you want a balance of sweet and acid, or the tart, and a little bit of salt and a little bit of fat, all of these things that go on our tongue. And that's exemplified in the fact that if you buy a fruit pie from the store, they're usually pretty gross, but if you make a homemade one, they're usually a lot better. And that's because the fruit pies from the store, they just dump a ton of sugar in there. And so all you taste is this sugary mush. But when you have a homemade pie, what you have is a little bit of sugar in the fruit, and hopefully the chef has picked a tart fruit. So if you're making an apple pie, you might want to put Granny Smith apples. And if you're making a peach pie, you want a type of peach that has a little bit of acid in it, a yellow peach and not a white peach, because those are just sweet. And the crust has fat and salt in it, and you get that lovely mix of flavors that is good for our tongue. So yeah, that's what the pH scale looks like, just in case you haven't seen a pH scale before. And you can also notice that it goes from 0 to 14. So 0, 7, and 14 should sound pretty familiar from what we've done before. Also, another thing over here, we've got battery, and so that makes sense when students think of battery acid because it's very acidic. But then sometimes students will ask, well, what about like alkaline batteries? Well, that's a different type of battery, and yes, that is basic instead of acidic, like our car batteries that have sulfuric acid in them. All right, moving on to the next slide. So pH is a measure of the concentration of hydronium. And remember that we use H plus and H3O plus interchangeably. And how we figure out what the pH is of a solution is we say that the pH is the negative log of the concentration of hydronium. So you can say negative log of concentration of H plus or negative log of a concentration of H3O plus, either way. Now, what if we have the pH and we want to go backwards and we want to figure out what the concentration of the hydronium ion is in the solution? Well, we would do 10 to the negative pH. So if the pH is equal to 3.6, and you wanted to figure out the concentration of your hydronium in the solution, you would do 10 to the negative 3.6. And how I do that on my calculator is I type in 10, and then I have this little key that has like a hat or a rooftop, and then I do the negative key, not the minus, the negative, and then I would type in 3.6, and then I would hit the equals key. So that's how I would do it on my calculator. Now, there's something else called the pOH, and pOH is kind of like KB, where it exists and we have to learn it, but we don't use it that often. But it's kind of fun to use. So the pOH works exactly like the pH in that it's the negative log of something. And it's the negative log of your hydronium, hydroxide, bad teacher, bad. It's the negative log of your hydroxide ions in your solution. And if you have the pOH and you want to figure out what the concentration of hydroxide is, you would do like you did up here with the concentration of hydronium, and you would do 10 to the negative pOH. So if we have a pOH that's equal to 9.9, how we would figure out the concentration of hydroxide would be 10, and then you'd hit that little rooftop key or the caret or whatever we want to call it there, and then you would say negative and then 9.9, and then hit the equals key. And that would give you some number times 10 to something, okay? All right, another equation that you guys need to know is that the pH plus the pOH equals 14. So there's that number 14 again. So zeros and sevens and 14 should definitely be sounding familiar to you guys. All right, let's do some problems. So what is the pH for a hydrochloric acid solution that has a hydronium concentration of 2.3 times 10 to the negative 2? Well, 2.3 times 10 to the negative 2, and that's molarity, probably doesn't mean a whole lot to you. Like, I have no idea what that is. So let's go ahead and put it into the pH equation. So for pH, we have the negative log of 2.3 times 10 to the negative 2. And when we put that into our calculator, what we're going to get is 1.638272. Now, for significant digits on pH problems, it's a little bit different. So you see how right here in this coefficient, we have two numbers. So when we have a logarithmic answer, what we want to have is the same number of numbers to the right of the decimal as we had in the coefficient of the original number. So we have two numbers in the coefficient of the original number. So we want two numbers to the right of the decimal in our pH answer. I know that's strange, but that's how it goes. So that would mean we'd have 1.6 something, and the 8 is telling us we would round up to 4. So the pH for this hydrochloric acid solution is 1.64. So does that mean that it's acidic, neutral, or basic? That would be acidic, because pH is less than 7, indicate that you've got an acidic solution. Now take a look at this number right here, your exponent. that says -2. So if you just take a look at the whole number there, just 2, and ignore the negative, that's going to give you a clue to what the pH should be about, okay, approximately. So if you look up there, you could go, okay, well, the pH is going to be approximately 2, usually a little bit less than that, and we can see that it is a little less than 2 there. Alrighty. So number 2 says, what is the pH of a sodium hydroxide solution with a hydronium concentration of 3.39 times 10 to the -10? Okay, so if we look at the 10 right there in the exponent, we can see that we're probably going to have a pH of 9 point something, so a little bit less than 10. And that should make sense because we've got a base in our solution. So we've got hydroxides floating around, and a pH of 9-ish should indicate basic solution. So we're on the right track. So again, we go ahead and we write our equation. So pH equals -log of the hydronium concentration. So we've got -log of 3.39 times 10 to the -10. And when we use our calculator and we figure that out, what we will get is 9.469800. Now we have 3 numbers in the coefficient of the original number. So that means when we give an answer for pH, we want 3 numbers to the right of the decimal. So we're going to have 9.4, and then if you look at the 9 right here and then look at the number next to it, the 8 is saying that you're going to round the 9 up. And that always freaks students out because they don't want to do a 0. But just think about this, okay? Because there's a 9 on the end, you got to round 69 up to the next number, which is 70, okay? So you're going to have 9.470, and that makes sense because we said it'll be a little under 10, and it's a basic solution, so it should have a pH that tells you that it's basic or alkali, and it absolutely does.